In this video, we are continuing with hypothesis testing. So here we're just going to focus on test concerning difference between two means. Now, if we assume that we have two populations that have mean mu1 for the first population and the second population has mu2 as the mean, their standard deviation, let's say for the first population have sigma 1 and for the second population has sigma 2. The null hypothesis and the alternative can be stated as the H0 will say that the mu1 is equal to mu2. Then the alternative hypothesis will say that mu1 is either less than mu2 or mu1 is greater than mu2. So this is for the one-tail test. For the two-tail test, alternative will say that mu1 is not equal to mu2. So when you see this, it is for two-tail test. So if it is used in English, it can be said test that the mean has changed. Here they can say test that the mean has increased or test that the mean has reduced for the one-tail test. Test that the mean for the first population is greater, is less than it's for one-tail test. These are the languages that can be used for one-tail test. So for other things, we can use x bar 1 for the sample mean of the first population, x bar 2 sample mean for the second population. We can use n1 for the sample size of first population. We can use n2 for the sample size of second population. We can use S1 for the sample standard deviation of first population, S2 sample size of second population. Now, for the z test, we have that z is equal to x bar 1 minus x bar 2 over square root of sigma squared 1 over n1 plus sigma squared 2 over n2. Here is when we know the sigma, the variances, the population variances of the first one and second one, we know them. So, but when we don't know them and the sample size is large, which means the sample size is n, they are greater or equal to 30. So, when they are greater and we don't know this, we estimate them for the sample standard deviation. We say S1 squared over N1 plus S2 squared over N2. Sample standard deviations. But in a situation where N is small and we don't know the sample standard, we don't know the population standard deviation, we use the t-test and say that t is equal to x bar 1 minus x bar 2 over pooled variance 1 over n1 plus 1 over n2. We use this, especially this pooled variance, when we are told that sigma 1 is equal to sigma 2 or that sigma 1 squared is equal to sigma 2 squared or sigma 1 squared equals sigma 2 squared. Whenever this is assumed in a question, we use this. And this is given as SP squared equal to N1 minus 1, comma, S1 squared plus N2 minus 1, comma, S2 squared over N1 plus N2 minus 2, and its degree of freedom is given as N1 plus N2 minus 2. V, degree of freedom. But in a case where they are not equal, the degree of freedom, the t-test will just be given as x bar 1 minus x bar 2 over square root of S1 squared over N1 plus S2 squared over N2. But the degree of freedom V will now be given as, it will just be a little bit complicated, S1 squared over N1, V equal to S1 squared over N1 plus S2 squared over N2 all squared over S1 squared over N1 over N1 minus 1 all squared plus S2 squared over N2 all squared over N2 minus 1. So this will be the degree of freedom for it. For example, this question says the random variables x1 and x2 follow the normal distribution with means mu1 and mu2. The variance is sigma 1 squared equals 225 and sigma 2 squared 180 respectively. Random samples of sizes n1 50 and n2 48 from the two populations have means x1 x bar 1 103.25 and x bar 2 96.5 respectively. Test at 5% level of significance the hypothesis that H0 states that mu1 minus mu2 equals 0 against the alternative mu1 saying mu1 minus mu2 is greater than 0. Okay, so for us to solve this, the first thing is to state this hypothesis they say we should test, which is H0 will say that mu1 minus mu2 equals 0, which means mu1 is equal to mu2. Then H1 says that mu1 minus mu2 is greater than 0. The next thing is to state the level of significance, which is 5%, which is 0.05, and that means that we're using z-test because the n is greater than 30. The two n's that we have, sample sizes, they are greater than 30. So the formula, we have z bar 1 x bar 1 minus x bar 2 over square root of sigma 1 squared over n1 plus sigma 2 squared over n2. If we fix the values, we have 103.25 minus 96.5 over square root of 225 over n1. Sorry, our n1 is 50 plus 180 over 48. And if we press the calculator on that, we'll get 2.35 approximately. So remember that from here, our z tabulated will be z 0.05. And the value for z 0.05 is 1.65 from the statistical table. So if we compare two of them by drawing the distribution curve, the middle is 0, and okay, here we have just the positive values, so we use the right side. Here is the boundary critical point, so the value we get is the critical value 1.65. So we have 2.35. If we plot it here, it's going to exceed 1.65. So let's say 2.35 may be around here, 2.35. So here is acceptance region, here is rejection region. So since this calculated value, z calculated, entered the rejection region, 2.35. So we see that since z calculated is greater than z tabulated, we therefore reject H0 and accept H1 and conclude that mu1 minus mu2 is greater than 0. The next question says two random samples are drawn independently from two normal populations with the following results. Sample 1 has this, sample 2 has this, sample size 16, sample mean. So he said at 5% level of significance, test the hypothesis that there is no difference between the two population means, assuming that the two populations have equal standard deviations. Now, this last phrase is very important. It says assuming that the two populations have equal standard deviation. Because of that, we're going to pool two of them. Since the standard deviations are equal, we're going to pool. And the sample size n is small, 16 and 20. So two of them, they are small. They are not up to 30. So because of that, we're going to use the student test T test, and t is equal to x bar 1 minus x bar 2 over square root of sp into 1 over n1 plus 1 over n2. And remember that we need to first of all find the sp. That sp squared is equal to n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2. So if we fix the values, we're going to get that the pooled variance is equal to 16 minus 1, 45 squared, because the standard deviation of the first one, plus n2, which is 20, sample size 20, the second one, 20 minus 1, standard deviation of the other one, 38 squared. So 38 squared over 16 plus 20 minus 2. So here, if we resolve all of them, we're going to get 1700.32 as our pooled variance. So if we now get back to the normal question, we have that our t calculated now equal to 260, that's x bar 1, which is the sample mean, 260, minus x bar 2, which is 210, over square root of the value xp pooled variance 1700.32 into 1 over 16 plus 1 over 20. So if we resolve all of that with a calculator, we're going to get 3.615 approximately. So since this is this, our t tabulated is now going to be, remember this is, okay, we did not state the h naught, which is the first thing that we're supposed to have done. So h naught will say that there is no difference, which means mu1 is equal to mu2. Then the h1 will say that there is difference, which means this is not equal to this, which is two-tailed test. So our alpha is 0.05, and since it is two-tailed test, we need to divide this into 2. So alpha over 2 is equal to 0.05 divided by 2 is 0.025. Need to turn. So what it means is that our t tabulated is t 0.025 comma v, degree of freedom, and remember that v is equal to n1 plus n2 minus 2, which is 16 plus 20 minus 2, and that gives us a total of about 34, right? Yeah, because this 36 minus 2, 34. That gives us 34. So what this thing means is t 0.025 under 34. So we go to the for t table v 34. 34 is greater than 30, so we're going to look at that under v. So 34 under 0.05, 0.025, I beg your pardon, 0.025 under infinity, 1.960. So the value is 1.96 or 1.960. So we compare this with our calculated value. Our calculated value was 3.615. So if we draw the distribution curve and we come here is 1.96. So at the middle is 0. So what we now have is, if we want to put 3.615, it will be around this place, 3.615. And you know this place is acceptance region, this place is rejection region. So since our value that we calculated is 3.615, therefore our conclusion will be, since z calculated is greater than z tabulated, we reject h0 and accept h1 and conclude that both means are not equal, because that's what the H1 says. So we reject H0 and accept H1 and conclude that the two means are not the same.